Okay, this is John Perham, your tutor here. Here's the solution to problem 8 from last week's problems. Anyway, Down syndrome is a disorder that affects 1 in 270 babies born to mothers aged 35 or over. A new blood test has a sensitivity, i.e. the probability of a positive test result given that Down syndrome is present, of 89%, and it has a specificity, i.e. the probability of a negative result if Down syndrome is absent, of 75%. So we're asked three questions. What proportion of women over 35 would test positive for this test? Part B, a mother receives a positive test. What is the probability that the syndrome is present? And C, a mother receives a negative test result. What is the probability that the syndrome is actually present? And there are two ways of solving these problems. One is using the formulas. I'll call that the calculus of probabilities. And the other is the method of brute force. And we'll do both of them. So anyway, the probability of a positive test is equal to the probability that Down syndrome is present, D, times the conditional probability that the subject tests positive for Down syndrome. And then the other contribution is from the people who don't have syndromes, the probability that they don't have Down syndrome, and then times the probability that they test positive anyway if they don't have Down syndrome. And from the data in the problem, that's the probability 1 in 270 times the sensitivity, and then plus the probability of not having it, 269 over 270 times 0.75. So let's execute that. And the answer comes out to be 0.25237. That's kind of straightforward. Let's go down a bit. The probability that somebody has tests positive, has Down syndrome, is this conditional probability here, and that value is given by the probability of D, that they have the syndrome, times the conditional probability that if they have Down syndrome they test positive, and divided by the probability that they test positive. And I'll show you where that result comes from, up here. If we take the definition of conditional probability, the probability of A given B, then that's the probability of A and B divided by the probability of B. And we can rearrange that to give us this. And then the probability of A and B must be equal to the probability of B and A. And so we have an alternative expression for the probability of A and B. It's the probability of A times the probability of B given A. And we can arrange that to give this formula here. It's kind of hinted at in the notes, but this is where the formula comes from. So we put the numbers in. It's the probability that they have Down syndrome, which is 1 over 270, times the probability that they test positive if they have it, and divided by the probability that they test positive, and we've just calculated that. So we execute that, and the numerical value is 0.131 or thereabouts. And then finally, we'll go to part C. The probability that a woman who tested negative had Down syndrome, well, that's given by this conditional probability that they tested negatively, but they actually had the syndrome. And using the previous formula, that's equal to the probability of D, that they have Down syndrome, times the probability that if they have Down syndrome they test negative, and then divided by the probability that they test negative, which is 1 minus the probability that they test positive. So we do all that, and so it's probability of D, that. The probability that if they have it, they don't test positive, which is 0.11, and then 1 minus the probability of P. So we calculate that, and it tells us it's a very small number. So that's the way you do those problems. You just have to be very clear about what probabilities you're talking about. There is another way to do them, which probably takes more time, but is kind of simpler. So I'm going to define 4 types of individuals for this problem, and they're the group of women who test positive and have Down syndromes, the group of women that have Down syndrome and test negative, and then those that don't have Down syndrome that test positive, and then don't have Down syndrome and test negative. And all the women in the sample will belong to one of those classes. So this is a useful function that I've built, and it enables us to define these symbols, follow the probabilities associated with each of these events. Well, now we want to get some connections. Well, first of all, we know that since these include all possibilities, that the probability of one of them happening, which is the sum of these 4 probabilities, has to be equal to 1. So that's the left-hand side of the fraction of each. And then we go down to the next equation. And the next equation says that the women, the fraction of women who have the syndrome is given by 1 over 270. If we go and look here, the fraction of women that have Down syndrome is this number here, the number who test positive plus the number who test negative, and they must be equal to the fraction of women who have the syndrome. So that's another linear equation. And then an equation reflecting the fact that a fraction of women, 0.89% of women with the syndrome will test positive. What is that? Well, the fraction of women with the syndrome who test positive is that, and then we divide that by this number plus the fraction who don't have it that test positive, which is this number, and that number should be equal to this, and then we put all that together and take the numerator, because that has to be 0, and that gives us this equation. And then one more piece of information, and that is that 0.75% of women without the syndrome will test negative. Well, that's the number of women who test negative who don't have the syndrome, and then divided by the number of women who do have the syndrome. No, hang on, let's go and look at that in a bit closer. The fraction of people who test negative and don't have the syndrome is this divided by this plus this. No, this plus this. And that gives us a 4th equation, and we put all those together, and then we've got 4 equations. All these 4 things are equal to 0. So they're 4 linear equations for 4 unknowns, and we can solve those using our techniques. We can view them all here. These are all equal to 0. Well, we've got linear equations, so we want to solve them, and we do that by our method of row reduction, etc. So we extract the coefficient matrix by this, and then we put that into matrix form, or show it in matrix form. That's the coefficient matrix. And then we can calculate the right-hand side vector by subtracting the product of the coefficient matrix with the variables and subtracting off the equations. And that gives us that. And now we build our augmented matrix. So we take each row of the coefficient matrix and we attach the corresponding element of the right-hand side vector, and that gives us that. And then we can look at that as a matrix like so, and we're ready to go. So let's have a closer look at the matrix. So the first step is to get zeros on the below the diagonal in the first column. So we subtract the first row from the second, and the first row multiplied by 0.11 from the third, and we don't touch the fourth row because it's already got a 0 there. So we do that. Notice we get a little round off error here. We'll deal with that later. That's basically due to the conversion between fractions and floating point numbers. So anyway, so this is now all zeros. Now all we have to do to put the thing into, well, almost, is to interchange the second and the third rows, because that will put a 0 there. So we do that. So we take the rows of a new matrix and we just interchange the second and the third, and while we're at it, we get ourselves a 0 here. So let's do that, and we can view that as a matrix. We didn't do that at all. Sorry, we do it now. We just subtracted the 0.75 times the first row times the second row from the fourth row. And if we look at that again, we can see that it's almost in row echelon form. All we have to do is to interchange some rows, the second and the third, and we can do that using this, and there it is. So you can see that this is now, apart from this round off here, is in row echelon form. So now we can apply the back substitution to find all the other things, or all the solutions. So we get the equation corresponding to the last row. We get that. So that tells me that the probability of a woman not having the syndrome testing negative is equal to that, and we can set that equal to 0 and solve for the fraction of women without the syndrome who test positive, which is that. Notice that that's not, test negative. That's not 0.75. And now we can now insert that solution into the equation corresponding to the third row, which we can obtain using that, and that gives us the value of that the Down syndrome is absent, but the person tests positive. And we can set that equal to 0 and solve it using that, and there we go. And now we continue. So we take the second row and we put our solutions for the third and the fourth variables into that, and that should give us an equation for the second variable. Well, it almost does, but remember we've got this round off error here, So the easiest way to get rid of that is to set this equal to 0 in this equation and then solve the result for this guy here, and we can do that, and we get that. And now we put all that into the first row, the equation represented by the first row, and we get that. And that is the proportion of women who have the syndrome and test positive. So we can solve that. And now we can work out the fraction who test positive, which is just the sum of the first variable, which we just found there, and the third variable, and we insert their numerical values, and that's the answer we got before. A woman tests positive, the probability she has the syndrome can be computed using the formula for the conditional probability. So this is the probability that she tests positive and has the syndrome, and that value is that, and that's what we found before as well. And then finally, let's go down. And the probability that the woman who tests negative has the syndrome, well, that's again a conditional probability. So we take the probability that the woman tests negative and has the syndrome, and then we divide that by the probability that she doesn't have the syndrome and evaluate it numerically using that, and we get the same answer we got before.